I will be talking about refactoring to Java 8. This has been a surprisingly popular topic over the last year or so, because we've seen presentations about how Java 8 has introduced new features like lambdas and streams and so forth, and we've seen presentations about how to use them in new code. But what's kind of more applicable to most of us as day-to-day developers is how do we take an existing code base and perhaps move it in the direction of Java 8, and perhaps also understanding some of the pros and cons of doing this and some of the trade-offs. So that's what this talk is aimed to answer. But first, before we do that, let's take a quick look at why should we move to Java 8? Well, Java 8 is now nearly 3 years old, so I'm guessing probably a lot of people are already using Java 8 or considering it, and probably one of the most compelling reasons is the fact that Java 6 and 7 are end of life and no longer officially supported. So it's a good idea to move to Java 8 just for those reasons. But there are some really compelling reasons to argue when you're trying to push your case to management or to the support team or to whoever inside your organization cares about these things, about why you should be adopting some of the Java 8 features. Firstly, Java 8 is generally faster than previous versions of Java. You don't even have to do anything or use any of the new features to get some of these speed improvements. For example, some of the common data structures are faster, there's some speed improvements around concurrency and so forth. And for more information about this, click on that link because there's some links to additional documentation about that. Of course, it's easy to parallelize. That's the point about some of the stream operations, the fact that you can run stream operations in parallel without having to manage things like thread pools or executive services or so forth. It can be done quite easily for you. You write fewer lines of code. As a hardcore long-term Java person, maybe this wasn't the most compelling reason for me, but in actual fact, once you get used to using the Java 8 style, you start to see that what you're writing is what you want to achieve, not how to do it. And that's quite nice. That takes away a lot of the boilerplate and stuff that your eyes were kind of ignoring and lets you focus on what's really important in the code. And the ability to do things like pass around Lambda expressions or use the Streams API gives you new solutions to problems and perhaps lets you solve things you couldn't have solved before. One of the areas I think is under publicized is that some of the Java 8 features let you minimize errors. We'll see some examples of where we can minimize things like copy and paste errors using Lambda expressions, but there are other things like optional and other features that let you minimize the amount of errors that accidentally creep into your code. Also, things like the Streams API and the added readability, reduction of boilerplates, can let you see much more easily where you've made a silly mistake. So let's go straight on into the refactoring side of things. But before we do any sort of refactoring, we really do need to have a safety check to make sure that we're in the right place to do some refactoring. Firstly, it's really important to have automated acceptance tests if you're going to do any refactoring, because although a lot of the refactorings I'm going to show you, the idea is the functionality will remain the same, you can't be sure that you haven't accidentally changed some functionality if you don't have automated tests that prove to you your code still does the same thing it used to do. Performance tests are important for the same sort of thing. And in fact, we'll talk quite a lot about the performance of some of these refactorings as we go through this talk. So you'll get an idea for perhaps how using Java 8 idioms impacts the performance of your code. If performance is important to you, it's important to have tests to prove that you haven't done something weird to impact the performance. And when I say performance is important, I don't necessarily just mean sort of nanosecond latency for high frequency trading or whatever. I sometimes mean things like responsiveness to the user in less than half a second, or something like how long does it take an Android app to make a call to the back end. So these aren't necessarily, I'm not talking about high performance, I'm talking about making sure that you have performance tests for the things that really matter to you performance-wise. Before you do any sort of refactoring, you really need to decide as a team, as an organization, why you're going to do this refactoring. And there are a number of different reasons. We've talked about things like performance and readability, removing boilerplate, removing errors. You can also do refactoring for learning. You might want to upskill the team on a code base, in a domain that's familiar to them, so get them used to using Java 8 idioms in an environment that's comfortable to them, rather than trying to get them upskilled on a new language with new idioms on a new domain, on a new project. So the idea of doing refactoring in order to upskill the team is also a valid thing to choose. Now, it doesn't really matter which of these goals you choose, but the idea is to have in your head what you're trying to achieve by doing this refactoring and stick to that. You should limit the scope of any refactoring you're doing. In these examples, we're largely going to look at the method level. So they're going to be small bits of refactoring that we're doing that has fairly limited scope. You might want to restrict things either to a method level or class level, but you certainly shouldn't go straight in and try to refactor the whole code base to use optional, for example. You really want to ring fence the area that you're doing these refactorings in. The code base we're going to be looking at is a project called Morphia. This is an object document mapper for MongoDB, and there's a few reasons why I've chosen this. Firstly, because I was working on it when I was working at MongoDB, so it's a code base I know very well. But more interestingly, it's an open source code base so that you can take a look at it for yourselves, see the before and after the refactorings. It's also a fairly mature piece of code, so it has a lot of the same characteristics you'll probably find inside a lot of your own code bases. Sort of bits of code that maybe have evolved in a suboptimal way over time, or bits of code where it's no longer sort of fashionable to follow those ways of doing stuff. So it's quite a nice code base for refactoring, as you can look at some of these chunks of code and think of better ways to do these things, especially using Java 8. So without further ado, let's dive straight in and start doing some refactoring. The first thing I want to look at is refactoring to using Lambda expressions, because this is probably the simplest and most automated refactoring that we can do. The easiest things that we can do is take any anonymous inner classes that implemented things like comparator, runnable, callable, predicate, all of these interfaces that always only had a single abstract method, and use Lambda expressions instead of using anonymous inner types. So let's go straight into our code. What I've done is I've run inspections on the Morphia code base. I'll take a quick look at this because I'm in a fortunate situation where I can actually show some of the IntelliJ specific features in this webinar. So I've got an inspections profile called Java 8, and I've selected a subset of the inspections. Most of the ones that I'm interested in are in the, let's find it. So I'm in Java. Most of the ones that I care about are in the, where is it? I've gone right past it. Language level migration aids. So here we have things like we're selecting to find anonymous inner types that can be replaced with Lambda expressions. There's a whole bunch of stuff around how we can replace loops with the Streams API, and a lot of other features here. So this is the sort of main set of inspections we're going to be running. I'm running a few more, and we'll see those as we come along. But this is where you want to configure them. So in inspections, in language level migration aids, you might want to turn some of those on. Now I've already run those. Let's have a quick look at the first set. This is anonymous type can be replaced with Lambda. And if we look at this example, we can see this is a predicate, a Guava predicate, and we have our anonymous inner type with our method. And IntelliJ can just automatically turn that straight into a Lambda expression. So that's a fairly straightforward piece of magic whereby we are going to remove all the boilerplate of our class declaration, our method, our type information, and just keep just the business logic, just the stuff that we care about, and put that into a Lambda expression. Let me show you another couple of examples. I think with the maturity that Java 8 is at, probably most people in this webinar have already come across these things. So I'm going to skim quite quickly over some of the introductory level stuff. So here's another example. This is an example where we have a runnable, and again, the runnable can be converted into a Lambda expression. And here we just get we just keep the core of what the run method is. What's a little bit more of an interesting example is this callable here has 2 lines. So when we shrink this down to a Lambda expression, you can see the 2 lines in the Lambda expression. And what I prefer to do personally is I like to extract these into a method and give it a description. So this is until 10 items found. And this gives me a couple of benefits. One, I can shrink my Lambda expression right down. I can also even maybe turn that into a method reference if the call is the correct shape. But mainly, this is much more descriptive. So now I can say until 10 items found. So it's much clearer to me what these 2 lines of code are doing. On top of that, if I have any errors or want to debug this, it's a bit easier to debug Lambda expressions if they're actually inside a method. So that's my main reason for making my Lambda expressions a single line long. So that's all fairly straightforward. What's kind of more interesting is those examples are anonymous inner classes that were implementing an interface. We can do the same thing with abstract classes, but we have to go one step further. So Runnable, let's take a look at Runnable. Oh, that's not the right shortcut. So Runnable is a functional interface. It's an interface with a single abstract method. And if I look in my code, I can find abstract methods that look fairly similar. So I have an abstract method with a single an abstract class with a single abstract method on it. And IntelliJ is suggesting that I can convert this to an interface, which I'm going to do. And then once I've converted that to an interface, I can tag it with functional interface. And then what I can do is I can go around and look at the implementers of this. And now I can turn these into Lambda expressions. Now I couldn't do that before because Lambda expressions don't work with abstract classes, only with interfaces. So that's just an additional step that we can do. So those 2 things are just taking your existing code and applying basically new syntax to the existing functionality that you had. So let's have a look at that performance. Here we've got one of those examples. So our anonymous inner class and our Lambda expression. And these are the 2 things we're going to compare in our performance test. So in our performance test, we're measuring operations per millisecond. So more operations is better. So I've got my smiley face at the top to remind me which is the better performance. So here we can see the Lambda expression outperforms the anonymous inner class. Not by a lot, it's kind of fairly equivalent, but the Lambda expression is better performance. Now, obviously, Oracle did a lot of performance testing around Lambda expressions, and there are lots of different types of anonymous inner classes and Lambda expressions. So the performance of them varies according to what you're doing. So if you are interested in the ins and outs of this, you can follow this link here, and that will take you to a much more in-depth document about performance testing these things. In this particular example, you can see sometimes the Lambda expression, which is the one in the sort of reddish color, is better than the anonymous inner types, and sometimes it's not better. So the answer is generally the performance is fairly similar, but it's not exactly the same. In terms of the performance analysis, are Lambda expressions faster than or slower than anonymous inner types? Well, they're more or less the same, which means that you can go ahead and refactor this automatically without worrying too much about it. But if it really matters, then obviously you want to measure each individual instance to make sure that it's not adding some performance overhead. Now that was a straight replacement of anonymous inner types to Lambda expressions. What's more interesting is some of the patterns we can follow now that we have the ability to pass around behavior and not just objects. So we're going to find some places in our code where we can start passing Lambda expressions. What I've done is I've created a structural search. Let's take a look at this structural search. So I've created a search which is going to look for a call on log of any level with any message. And what I want to do is I want to replace this with something which takes a Lambda expression. And I'll show you why in a minute. If we look at one example of these, we're doing a log.debug. Now, normally, in most of your code bases, you'll see something like this. If log is debug enabled, then do that. And there's a reason for that, because obviously the check, the if, could be inside the debug method, and in fact probably is as well. But the reason to wrap it in the if statement here is that here you're actually building up a string, you're creating a new string. In this case, this stages field is a list. So it goes off to that list and builds up a string which is a representation of all the items in that list, and then appends it to the stages thing, and then calls the debug method with that string. Now, if you're in production, you are probably not logging at debug level, so you've just incurred the cost of building up that string when you don't need it because you're not actually logging at that level. Now, there's an alternative way of doing this. So if instead we pass in a Lambda expression, what we're doing here is we're passing in the recipe of how to create that string, but we're not creating that string just yet. We're going to do it lazily. So let me remove this here. By the way, if you want to know what shortcuts I'm using, they are flashing up down the bottom of the screen. You can see which shortcuts I'm using to try and navigate quickly. So here I'm going to create this method. It's going to take a supplier of string. Let's call it string supplier. This logger interface is implemented by a number of different implementations. Now, what I don't want to do is I don't want to go into every single one of those implementations and create the same implementation of this debug method, because I actually know what this debug method should do. So let's create another thing which is new in Java 8, a default method on my interface. And this, oops, I've accidentally got rid of that. And then this default method is I'm going to do the check for whether the debug is enabled there, and then I'm going to do debug string supplier.get. Now, the difference here is that it's only at this point that we build up that string. So it's only at this point we incur the cost of creating that string. And what's nice about putting this as a default method is that this is now inherited by all of the implementations of this interface. I don't have to put that implementation on all the individual implementations. So that's good for performance reasons. We'll have a look at the performance, so you'll see that in a minute. But what it's also good for is reducing things like copy and paste errors. Let me show you an example of this. So here's an example of a debug statement that's in the code, and it says log.isTrace enabled, but it actually logs at info level. And this is not uncommon in terms of copy-paste errors, the fact that we're going to copy this from somewhere else and then maybe change the level of the log. Now that we can actually pass this in as, now that we're doing the if statement inside the info call, for example, then I don't need this. And I know that I'm doing the right thing inside the method. So I'm reducing these copy-paste errors by passing these Lambda expressions around. So not only do we have an impact on performance, but we also are potentially reducing some of the errors too. So let's look at the performance of this. Here I've got a performance test which is testing 4 different cases. One where I'm logging with a constant string, which is always the same thing. 2, where I'm logging with a Lambda expression, which also has a constant string. The third one, where I'm logging with a string which is changing. I'm going to be appending some new value to the end of that. And you can see it's just a really simple change. And the fourth one, where I'm passing in a Lambda expression with the same thing, but this one will be lazily evaluated inside the log. So that if we are not logging that string, we don't incur the cost of creating it. And we can see here that the performance here is very significant. When we actually have to create the string that we don't need, we get very poor performance from that particular test. So that by introducing the lazy evaluation using Lambda expressions, we have got quite a quick win for performance in our code. So this is a good thing to do. We should definitely try and think about where we can use Lambda expressions for lazy evaluation. That's kind of all I really wanted to talk about explicitly around Lambda expressions. I've got way more to talk about around collections and streams because there's quite a lot of opportunities for refactoring to using the new methods on collections and the streams API. The first and simplest thing to do is basically find everywhere where you were using a for loop before and replace it with a for each method. Now, collections themselves have a for each on, so you don't necessarily have to use the streams API. So sometimes it's .stream.forEach, and sometimes it'll be simply a .forEach on your collection. And we'll see different examples of these. Let's go back to our code. Here what we've got is we're looking for loop can be collapsed with the Stream API. If we look at our first example, here it says that this can be collapsed with a for each. So if I do this, do Alt-Enter, replace it with a for each, then I've quite simply removed my for loop entirely and just replaced it with a for each with the name of the method I want to call for every entity in that set. Now I can go one step further now because I realize that this entity's variable is only used here, so I'm going to inline this. And then once again, this R variable is only used here, so I'm going to inline that as well. So I've actually just removed a lot of boilerplate there, and all I'm really doing is, instead of this for loop, I use a for each, and I'm going to call this this map method here. So that's quite simple example. Let's take a look at a slightly more complicated example. Here we have a for loop, followed by a for loop, followed by an if statement. And inside this if statement, we're going to add things to another collection. So let's see what IntelliJ suggests. We can replace this with a for each. Now let's dissect this a little bit. Our for loop has been replaced with a for each. If has found its way into the filter. We are calling this on a stream. And we're actually using map to create this new constraint violation thing, which is the thing that needs to get added into our set. So we've collapsed this for and if into a filter, map, and for each call. Now I'd be tempted to simplify this a little bit more just for readability. I might call this create violation. But that's totally up to you, really. So we've managed to simplify that code a little bit, but we still have this outer loop here. So for me, I would look at this and think, well, maybe there's something around the design which isn't great, because what we're doing here is we're passing in another collection and then doing some iterations, multiple iterations, because we're iterating here. This is effectively an iteration, and then we're adding stuff into another collection. So I would look at this and I'd be thinking, well, perhaps this refactoring needs to take a step up, take a step back from this, and look at the methods which are calling this method to see if things can be restructured to be able to do this in a single stream operation. Let's look at another example. Here we have an if statement, a for loop, another if statement, a for loop, and then an if and an else. So this is quite a complex piece of logic. Now, because we have an if and an else, we have two code paths there, so we know that this can't be collapsed down into a single stream operation inside here. But we'll see what we can do here. Now, IntelliJ has taken a look at this and decided it can do a slightly more complex thing. So because we've got two for loops, we've effectively ended up with a for each and a flat map. And the flat map is as a result of that second for loop there. And the if statement has been refactored towards the filter. So we actually have the same functionality, the same features, just in using the Streams API. So what's interesting here is to performance test the difference between the classical for loop and the new for each, whether you're using streams or not. So this is our first example, our simple example, where we replaced this for with a simple call to for each. And here we find the performance is pretty much exactly the same. So we don't really need to worry too much about whether we decide to do this or not. This more complex example, which uses the flat map as well as the filter, again, the performance is kind of more or less the same. So we can make decisions as to whether we want to do this refactoring based on performance. We could say it doesn't really matter. We can apply this refactoring if we want to, but we still have to look at this and decide whether we think this is more readable, because we do still have another if statement outside here, and we do have this quite ugly if else inside here. So to me, there's room, in terms of readability, there's room for additional refactoring there. We can't expect the IDE to just magically do this for us. And the third example, where we removed this for loop and this if statement into a filter and map, the performance here is quite a bit worse on the refactored code. Now it's about it does about half the amount of operations per millisecond. It's not a factor of 10, but it's not ideal. That it's not exactly the same performance. And this might seem quite puzzling because it's still doing the same thing as some of the other examples. In fact, arguably it's doing slightly less because there's no flat map and it's not such a complex example. However, if you look at the performance of these, this one, for example, we're getting 0.6 operations per millisecond, which is not very many operations. So it could be that the thing that's happening inside the loop is quite expensive, and the cost of iterating over the loop is not the most expensive thing in this code. Therefore, whether you use a for loop or a for each doesn't really impact the overall performance. Whereas here, you're getting nearly 1,000 operations per second, in which case it might be that using the Streams API has added an additional overhead to this, to iterating over these in particular. So is it a given that you're going to refactor any for loop into using a for each? Well, no. Sometimes it's going to be fine performance-wise, and sometimes you're going to have to think about whether it gives you anything in terms of readability or performance. The next thing that's quite straightforward to refactor is turning a for loop into a collect statement. So if we have a look at this example, now here we have a slight complication in that what we're doing is we're iterating over a list of keys and we're adding the IDs into a list of IDs. So this sounds like a classic problem for collect. However, this array list is being initialized with an initial capacity, which means that IntelliJ can't automatically turn it into a collect statement. So I'm going to assume that this well, actually, I'm going to test to see whether this has any performance impact. So to begin with, I'm going to remove that initial capacity so that I can refactor this more easily. Now I can replace that with a collect statement, and I end up with a kind of classic collect, where I'm going to map from the key, just get the ID, and return a list of IDs from this list of keys. Let's look at another example. So in this example, we're doing something fairly similar. We are populating a list of valid fields with some subset of fields from this fields list. And we can actually see what we're trying to do. We're going to ignore static and final fields. So, oops. Let's get IntelliJ to replace this with a collect statement. Now, what I would like to do is I'd like to get rid of this comment because the comment says the code's not really very clear. So in fact, what we can do is we can improve this by extracting that into a method. Let's call this is not static or final. And then we can get rid of this comment completely. I would argue that in this case, this is more readable. So we're filtering out the only things that we want are fields that are not static or final. And we're collecting these into a new list and returning that list. So it's a bit more readable than it was before. We've also removed some of the boilerplate, and obviously there's comment. So let's look at the performance of this. The first example, what I wanted to do, as I mentioned, is I want to performance test whether this initial array allocation has any impact on performance. So I'm testing it with the array allocation and without it. And then I'm testing the refactored code with the map and collect. And what we find in this particular case, for a list of 10 elements, which isn't very many, that the original code with the pre-allocation of the array list size is much more performant than any of the other examples. It performs better than the simplified code without the array size. It performs better than the refactored code, and parallel with 10 items, basically, let's not even talk about it. It doesn't even appear on the chart. If we add a few more elements into the list that we're iterating over, so in this case 10,000 elements, then we see that the initial allocation of the list size really starts to make very little difference, and parallel starts to become much more performant. But our refactored code is still not performing quite as well as the other examples. Again, we're not talking about orders of magnitude, but it does perform a little bit poorer. The other example we looked at here was being able to get rid of this comment by replacing it with a filter and collect. Now here, the refactored code performs worse than the original code as well. In this case, I think it's because you're doing an arrays.stream. So you had code that was an array, and now you're having to do arrays.stream. So it's probably not going to be as efficient. We'll talk a little bit more about this a little bit later on. So automatically turning your code from a for loop into a collect statement, you're going to have to be careful a little bit about the performance of that code. So if you really care about performance, you're probably going to want to write some tests. Now, here's a good time to talk a little bit or have a little bit of a caveat. In the grand scheme of things, some of these performance implications may be pretty much nothing. Like I said, we're talking about maybe half the speed, but we're talking about micro benchmarks. I'm benchmarking just this method. In this particular case, this code actually is about code which goes off to the database. So the cost of talking to a database is probably substantially more than the cost of adding, than some of the additional cost added by using the Java 8 features. So micro benchmarks are useful, but you have to consider stuff in the grand scheme of the whole application, which is why it's important for you to have performance tests, automated performance tests for the code paths that matter the most to you. Now here's an area where I think streams are very interesting, where we can look at code which was previously a series of operations and collapse them down into a single stream operation. Here's our first example. We have a set, it's a set here, of constraint violations, whatever they are. We're going to iterate over those, add them into a new list, and then we sort that list, and then we iterate over that list and do something with it. So we should be able to collapse this down to a single stream operation. So IntelliJ says that we can replace this with a collect statement. Note that it has figured out that because you have a sort call here, it can add sorted here. And this is a fairly new piece of intelligence in IntelliJ. Some of the older versions don't make that leap. So it's worth bearing in mind that if you have a sort call, you want to make sure that your stream operation is also sorted. And then what do? So then we take this list and then we iterate over it and do something. So that seems to me like perhaps we can replace this straightforwardly with a for each. We'll do the same thing that the for loop was doing. So we do logline.log. And of course, we don't need to allocate this to anything because it's not doing anything anymore. And then we simply remove this. So we originally had an iteration here, some sort of iterating happening in the sort probably, and another iteration through the list here. And we've collapsed this down to a single stream operation. So it's a bit neater and a bit more understandable. And hopefully we should see some sort of impact on the performance. The second example here is in query impl. Now this might not look like multiple operations, but what you're doing is you're iterating over this collection, you're assigning stuff, adding them to another fields list, and then you're doing fields.toArray and passing that into another method. So you're doing at least two operations there. One, you're iterating over a list and creating a new list, and two, you're then turning that list into an array. We can actually see what we can do to improve this. Again, we have an initial capacity on this list, so it's not straightforward to turn it into a collect straight away. I'm going to remove that initial capacity. And then I'm going to replace this. It says replace with toArray. Now, this is some magic that I think this particular refactoring did improve in IntelliJ 2016.3, and I think it's got even smarter in 2017.1, because when I demoed this last time, I still had to do some manual steps, and now I don't have to do any manual steps. And what it's done is it's taken all of my original code and pretty much completely rewritten it. Now, I removed this, this size allocation for the array list. It's using the get name to store, it's putting that into a map, And then it's worked out that what I've done here is I've added things into a list, and then I call toArray. So IntelliJ has collapsed that straight down into a toArray call and inlined that into the retrieved fields method call as well. So there's quite a lot of stuff going on in there. And you might want to do, with some of these operations, you might want to do them in incremental steps to see what's actually happening. So in our first example, where we had sort of 3 operations collapsed into one, the performance here, not surprisingly, the refactored code performs better than the original code. Not by millions of orders of magnitude, but it does perform better. So this is good. It's more readable and marginally more performant. Now, this second example, like I said, there's a sort of naive intermediate step for refactoring this, where you might say, I'm going to collect everything into a list and then call toArray on it. So I wanted to performance test that to see what the impact was here, because this is basically 2 operations. We're doing a collect and then a toArray, which is the same as the original code. And then I want to compare that against the new complete refactoring, where we go straight to toArray. And here we can see that the naive refactoring with the 2 steps doesn't perform as well as the other operations. And the fully refactored one performs almost as well as the original. And this is at quite a high number of operations per second. So this is quite a good refactoring in this case. I've had to say the performance analysis is inconclusive, even though I'm much happier with these results than the other ones. Because again, we're not talking about orders of magnitude better, but the findings here is that we don't have a negative impact on performance by doing these particular refactorings. Now I've just got 2 more refactorings to show, and then we're going to sort of take apart some of the things that we found and come to some conclusions. This for loop to any match is a new refactoring which came in 2016.3. I'll show you an example. I've lost it. It's here. So AnyMatch is a fairly straightforward operation. It's where you are going to be looping through some list, and as soon as you find something which matches some criteria, then you return a true or a false. So this can be automatically turned into an AnyMatch operation here. You can see again, we just got rid of the iteration code and kept the main core code that's in the if statement. So here I'm going to performance test the difference between the original code, the new code, which is, it's more readable, but of course the interesting point about a lot of these Java 8 stream operations is the ability to parallelize them. So I'm going to performance test this against the parallel version as well. Now the original code performs pretty well, and the refactored code, this is for 10 values in the list. The original code performs pretty well. The refactored code is not even half the speed, and parallel for 10 values is nowhere to be seen, because the cost of splitting up a 10 value list, running over multiple cores, and then bringing the results back in is just far too much overhead for that number of values. Where it starts to get a little bit more interesting is where you have 10,000 values in this particular list. But again, we don't really see any great performance improvements here. And I think in this particular case, I think it's because we're using arrays.stream. And iteration over arrays is a much more, is a nice efficient thing to do for compilers and for the CPU. It's a very predictable thing to do anything with a straight array class. And so when you incur the cost of turning that into a stream and start dealing with objects, you're going to end up with quite a lot of additional cost. And you can see that in the performance here. The performance really suffers from using streams instead of using the straight array. And when we get to 100,000 values in here, then parallel starts to outperform refactored by quite a lot more. But again, we're still not really seeing the performance of using raw array manipulation. So AnyMatch, I've said questionable, but it's not the fault of AnyMatch. It's actually the problem of using arrays.stream. Doing any sort of operation on arrays.stream is probably going to be much more expensive than doing operations directly on an array, particularly for small arrays. And find first. So this is a very similar thing to any match. If I find my example, this is again where we're going to iterate over some list, and once we find the first thing which matches some criteria, then we're going to return that thing. So we can replace this with a find first. In this case, let's inline that. We are doing an arrays.stream. We could also slightly simplify this by saying stream of. It does the same thing, it just it kind of reduces the amount of code on the screen, so that's why I prefer that particular example. And so here, yes, again, we've just removed everything from the if statement and put it into the filter. Another example of this is in my converters. I'm going to do the same thing. Here we are doing, on the previous example, we had to create our own stream of a set of classes. In this example, oh, I've lost it now. In this example, we're doing a stream. We're getting the stream from this collection, which is a list. And here we can see we are explicitly stating what to return if we don't find anything. So there's some readability gains there as well. So let's do a quick check of the performance of this. Find first is, again, not performing quite as fast as the original, in particular here because we're doing an arrays.stream. I wanted to test the difference between doing arrays.stream and stream.of, and the performance here is exactly the same, so pick whichever one suits you. In the second example, where we're using the Streams API, we just don't get the same sort of performance that we got from the original code for an array of 10 elements. As we start to get much bigger data, that's where we start to see the benefits of both going parallel and perhaps using the refactored code. So again, find first, in terms of performance, it's worth testing that to see if you've got any sort of impact on your performance for that, particularly for small arrays. My final example is removeIf. This is one of my favorite examples, and I hope you'll be able to see why. Here, what I've got is I've got some set, helpfully called S, which I'm iterating over, and then I'm pulling the iterator out. I'm using a while loop, which I haven't seen for a while, to remove everything from the iterator which matches some criteria. And I can replace this straightforwardly with a simple removeIf, where I pass in the parameter of the thing I really care about. And here we just get rid of all of this nonsense of how to traverse the collection, of how to get the next item. We just don't care about that. We just pass in the Lambda expression of remove everything which matches this particular pattern. And if we also have a look, so here you can see I've just got rid of all of that boilerplate. If you look at the performance, it actually performs better as well. So out of all the refactorings here, this is my favorite one. You get better performance and you get more readability as well. I've had to say it's inconclusive because the performance is not sort of, orders of magnitude better. It is just marginally better in this particular case. Let's go through and summarize these findings, because I've kind of flung a lot of different refactorings at you and a lot of performance data. So I really want to summarize those things before giving some sort of conclusion about refactoring to Java 8. And then after that, there will be time for questions. So refactoring to use Lambda expressions instead of, for example, anonymous inner types is very easy to automate. And it's pretty safe performance-wise. You're going to get more or less the same sort of performance. So you can kind of, under most circumstances, just go ahead and do that without worrying too much. Designing for Lambda expressions, so for example, using Lambda expressions for lazy evaluation could give you a big performance benefit. In the example of in the logging example, if you don't need to incur the cost of building up the string because you're not going to log it, then wrap it inside a Lambda expression and you're going to get much better performance from that. generally, using the new idioms, the new methods on collections, the Streams API, Lambda expressions, and so forth does increase readability. I've got a few examples here. For example, obviously, the obvious one is Lambda expressions versus anonymous inner classes. It just removes all the type information that you don't really need. Using a collect instead of using a for loop and adding stuff is a little bit more descriptive. The AnyMatch is again a bit more descriptive, a bit less code, but it's not so much about the a bit less code, it's more about what is this thing doing? Well, it's just telling you if anything matches this particular criteria. And the same thing with `FindFirst. `FindFirst just allows you to state, this is the thing we're looking for, something with this annotation. And of course, `removeIf, you just lose a whole lot of boilerplate and you're left with only the thing you care about, only the pattern that you want to remove. And then when you're doing multiple operations and collapsing those down into a single stream operation, you get quite a lot of wins. So instead of having to have 2 for loops with a sort, you just have a single stream operation which does a map, a sorted, and a for each. And so that's much more easy to reason around and probably better performance. And again here, this is where we were doing multiple operations without really realizing it because we were collecting stuff into a list and then doing a to array on it. And here we've just turned that into a single operation. But you do need to be aware of the performance. Now, I'm not saying you have to micro benchmark every single instance of these refactorings, but you do need to have an understanding of which of them might have an impact on performance and which ones you might need to go away and check and test for. For example, anywhere where you're going to be using arrays.stream is probably going to be slower than using an array. As I said, operations on arrays are very efficient for computers. They're easy to reason around for the compiler. They're easy for the CPU to reason around. And in memory, all of those array objects are next to each other too. So array operations, traversing arrays, is a very efficient operation. So arrays.stream may be taking away some efficiency. So this is one of those examples where the using arrays just gave you much worse performance than the original code. Using the for each or the collect might be slower than iterating over a collection. This is where the answer is it depends. So there are some cases where using the for each gave you sort of half of the speed that you had before. And some cases in the past where you get the same sort of performance. This is where it depends a bit on what you're doing. What's the cost of the operation inside that iteration? And parallel is not going to magically give you speed improvements. Parallel is not some magic incantation which will just do all the hard work for you. It will give you speed improvements if your data is very big. For example, here we've got 10,000 elements. We're starting to see where parallel is giving us some benefits. And if your operation is very expensive, then you might want to use multiple CPUs and farm it out over multiple CPUs. Those are the cases where parallel is going to be useful for you. And sometimes with these Java 8 features, you get improved readability and better performance. So for example, in my particular example, it was the `removeIf. We got better readability and we got better performance as well. So let's conclude these. Should you migrate your code to Java 8? Well, of course, it depends. There's never a straightforward answer to any sort of technical question. So it depends. You have to remember what the goal of your refactoring was. Was your goal to get better performance? In which case, obviously, you're going to need to test that performance. If your goal was readability or learning, then you need to check whether the refactoring has given you better readability or whether you have actually learned anything from doing these refactorings. So you should be comparing the results of your refactorings with the original goal that you had in mind. You need to understand which things might impact performance, like using arrays.stream. And if you're not really sure which things are going to impact performance, you need to measure that. Your tools, like, for example, IntelliJ IDEA, can really help you automate a lot of this process and can suggest things to you that you didn't know was possible. But you do need to be able to look at what it's doing, figure out if perhaps there's a performance impact. You need to look at it and see if actually this does help you in terms of readability or it doesn't. And some of those examples that we showed, the refactoring was really indicating that perhaps there's a bigger design issue to address before we do these low-level refactorings. So all of the reference material is available at this link here. There's a lot more information about Java 8. There'll be a link to this video on there. There's links to slides. There's links to the code. There's basically all the resources for this talk are available here. And now is a good time to stop and take any questions that perhaps haven't been answered yet.
Okay, thanks Trisha for a great presentation, and let's look what questions we have. I see a question, why would an anonymous in a class be any different performance-wise to a Lambda? Are they not equal once compiled?
Right, well, the short answer is no, they're not. It does look like Lambda expressions are syntactic sugar over anonymous inner types, but they're not. They're actually different under the covers. Look for Brian Getz's presentations because he does like a whole hour on why they're not the same thing. Oracle worked really hard to make sure that Lambda expressions are not worse performers than anonymous inner types, but under the covers they're not the same thing. Because basically a Lambda expression is not a full class. An anonymous inner type is a full class with like headers and memory allocation, and it's a full-blown object, whereas Lambda expressions aren't.
Okay, the next question, why do we need to change our code? Why isn't it handled by compiler? If it could be handled by JIT, then we would not need any refactoring. If it could be refactored by the IDE, then it could be handled by JIT.
That's a really interesting question. I think probably the short version is that when IntelliJ suggests a refactoring to you, it is not saying that the new code is exactly the same as the old code under the covers. IntelliJ is suggesting new syntax to use, or different alternative syntax to use that will achieve the same aim, but under the covers it's not compiled down to the same bytecode. In particular, some of those refactorings, the two array one, let's see if I can find it. It's on the slides better, hold on. Yes, this one. This code here on the right, it does the same thing as this code on the left, but it's not the same code. It's not. There's one step missing. We're going straight from a map to a two array. So the compiled code is not the same thing. And that's because IntelliJ gets to suggest to you, the developer, this is something I think that does the same thing. In terms of behavior, it provides the same behavior as the original code. But I need you, the developer, to decide whether or not this is something that you really want to apply. Because as you saw with some of these, the performance shows that these are not the same operations under the covers. So you need to be able to, you need to be the one to make those decisions. And the JIT probably can make decisions for some of, not some of the examples I gave, but for some things. But the JIT is not going to go away and say, oh, well, I think that this should be an arrays.stream operation, because it's clearly not more efficient. Some of these refactorings I'm suggesting are to aid us, the developer, to read things, to give greater readability to the code, not to aid the JVM to run faster.
Okay. Next question. Should we prefer method references instead of Lambda syntax?
Oh, I like that question. When I first started doing Java 8, I really disliked method references. I thought this weird double colon thing was kind of unreadable and difficult to get my head around. But I have generally, over time, come to prefer method references over Lambda expressions where IntelliJ suggests that I use a method reference. And there's a few examples of this which I prefer. So in this example, the map is not so useful, but let me see if I can find an example of filter. Let's say we have, I find something with a filter. So let's say filter, I might say, what have we got? We're getting a key. I might say T key is not equal to null. And that's kind of fine, but IntelliJ suggests to me that I can replace this with a method reference, which says objects non-null. Now, in this case, I much prefer the method reference because I think it says to me very clearly, I want you to filter for all the non-null objects. So I know that the only objects I'm getting in this map operation are not null. Whereas in the previous version, I have to literally, it doesn't take me very long, but I have to reason around what this means. Like not equal to null or equal to null. Does that mean the not equal to ones are going to go through or they're not going through? And there's another example where I really like this as well, which is, let me see if I can I do sorted comparators dot comparing, and then I can do something like, oops, what have we got on T key? Get ID. Oh, well, that's not a great example because I just pulled it out of the air. But with comparator.comparing, you can use a method reference to say, this is the method I want you to compare on. So instead of having to do comparing like o1.getID minus o2.getID, or was it o2 minus o1, I'm not really sure. The comparing with a method reference to me makes it really clear that this is what I want to compare on. I'm comparing them on ID. And also I can do reversed, which says, okay, well then I can really easily sort descending or sort ascending. And so that's some of the places where I really like method references. I personally prefer method references over Lambda expressions most of the time, but basically it's going to be whatever seems to be the most readable for you.
Okay, thanks. And next question, can you provide more details on the benefits of moving to Java 8 without performing any refactorings?
So I'm going to assume from that question, it's like if you've got an existing code base and you're going to run it on Java 8 without making any changes. So without applying the Lambda expressions, without using the Streams API. So basically Java 6 code running on a Java 8 compiler and VM. That's what I assume. Now the benefits that I showed, let's go back to the beginning, all the way back. Yes, here we go. This is like the third slide. So a lot of these changes, so performance improvements in common data structures, changes to support concurrency, a bunch of these things. And again, there's links to more information from the page that links to. These speed improvements in particular, you get those without having to do anything, particularly because things like HashMap performs better. So presumably you're already using HashMap inside your Java 6 style code. Moving to Java 8, HashMap will generally perform faster without you having to do anything.
Okay, next question. How would you approach a situation where you need to iterate over a stream multiple times to perform different operations on it? Collect to a collection first and then perform the processing? Or is there a better approach?
I'm not sure. I would like to see the actual code example, but I think that some of these refactorings that we saw here, some of them are a bit magic and you just kind of get 3 steps in one. It just does it all for you. And I think that as you're getting to grips with some of the Java 8 features, it's important to do things incrementally. So if I was thinking in terms of a collection or some object requiring multiple operations to be performed upon it, I might write that in the code as, let's say, 3 separate operations. And then I'd have a test to make sure that's working. And then I might see if I can refactor it into either a single stream operation or, I'd see if I could refactor it into a single stream operation. You should be able to reason around which things are inhibiting that. So if I look at some of my examples, like this example, I know that there's another for loop here, so I feel like this should be able to be refactored into a single stream operation. But I know that the way that this is structured right now, I can't do that because it's this mapped field which I need access to here and here, which stops me from inlining this for loop. And similarly, I have to do a for each instead of doing something more streamy because I'm passing in this set. So the problem with this particular method is I have a number of collections that I'm doing stuff over. So I've got this found names thing, and I've got this set here, and I've got this mapped field thing, which also has lists inside it. So I've got a number of different collections that are interacting with each other. So I'm having to iterate over all of them. And in this case, I know that in order to perform that as a single stream operation, I need to get rid of some of those collections or collapse them in together. So the answer is, of course, it depends, but I'd be tempted on the first pass to write stuff out as a series of individual operations and then see if I can figure out which of those will collapse down into a single operation.
Okay, good. Again, a question about comparing method reference to Lambda expressions, but now performance-wise.
Ooh, I don't. Well, I was going to say I think they're the same. I don't know. I think there is some. I think there's some literature from Oracle on that, but I think they perform the same. I don't know. I shouldn't say anything because I don't know. I did look it up once. I can't remember.
Okay, so there are a couple of questions about the performance issues mentioned. First question is the lower performance is attributed to arrays.stream only? How about collections.stream?
Right. So the worst performance results that we had were definitely around arrays.stream. I'm just going to try and see if I can find some of these examples. Now, so let's find the worst ones. Right, so this is one of the worst examples. This is where we were using arrays.stream, and regardless of whether we were going parallel or not, we just couldn't get performance which got anywhere near the original array. And in this case, I believe that's because iterating over arrays, like I said, is very, very efficient, and it's going to be very difficult to match that performance. But there are other cases, as I think you're pointing out, where that's an arrays.stream as well. So this is a map and a collect, and it's not using arrays.stream. This is collections.stream, and it still is not as good performance-wise. Should we have a look at the code? Here we go. It's just keys.stream. And so the using streams does have an impact in terms of object creation. It does have an impact in terms of performance. So it's not just there is no free lunch, of course. So yes, there is a cost to using streams directly, not just arrays streams, but the arrays.stream is particularly bad, which is why I called that out.
Okay, and another question about this is, are these performance issues possible to be solved in future versions of Java, like 9 or 10?
Yeah, so the performance of Java 8 has been getting better, even just Java 8. So you get all these different updates for Java 8. I think I'm running release 112, whatever that means. So even without having to go to Java 9, we're getting improved performance under the covers. We're getting improved performance for things like Lambda expressions and so forth. The Streams API, one of the nice things about the Streams API is because how it's implemented is hidden away from you and you just interact with what you want to achieve, they can continue to iterate over improving the performance of the Streams API without impacting you using the Streams API. They can do that under the covers. So that's definitely going on. There's all sorts of other stuff coming into Java 9 and Java 10 which will improve the performance too. One of the things I do want to emphasize though is that even in a case like this, where it looks like this refactored code is really horrible performance compared to the original code, I did say it earlier, but it's worth reiterating. Micro benchmarks like this don't necessarily mean that your application is going to perform slower if you do this refactoring, because in the grand scheme of things, your application does a lot of other things. It talks to other services, and network calls are expensive. You know, it talks to databases. It has to respond to the user. There's all sorts of other stuff happening. There's lots of interactions between things. So the fact that these 3 lines of code or whatever don't perform quite as fast as the original lines of code may not have any impact on the overall performance of your application as well. And you might find that some of the improvements around things like garbage collection, some of the improvements around the speed of some of the collections that you're using, they might offset some of these performance tests which show that the performance isn't quite as good. So you need to measure stuff in the overall scope of your whole application, not just these micro benchmarks.
Okay, one more question about performance of lambdas and anonymous classes. Are lambdas bad or good for performance, or it depends on how we implement them? It seems like it's all about readable code versus better performance.
It does feel a bit like that. I would say that so my example of the Lambda, of using the Lambda expressions, let's go back. My Lambda expressions performed better. So in a whole bunch of cases, in this report here, there's a whole bunch of cases where the Lambda expressions perform better than the anonymous types. So you get increased readability and better performance. I actually had to search through this document to find one example where the Lambda expression didn't perform quite as well as one of the anonymous inner types. So for Lambda expressions in particular, they are, Oracle worked really hard to make sure that they were no worse in performance than anonymous types, and they're often better. And as I said, the performance of these is getting better as well because of optimizations to the JVM itself.
Yeah, thanks. One more question. Since results for parallel are calculated in isolation, would it make a difference if we do parallel in production app? I guess then with parallel, I might be consuming or using threads that could have been used for other operations. I'm not sure if that completely clear.
I'm not sure if I quite understand the question. Is the question, is running parallel in production different to running parallel in these tests?
As I understood the question, it is, let's say we use parallel, so we leverage other threads, and so we wonder if we affect the performance of the application by doing that, considering we consume the thread which could be used for other operations.
I don't think it works that way. Maybe I'm misunderstanding the question, but what Parallel is doing is, under the covers, it uses the fork join framework. So it will be spinning up, if you like, its own threads and running. The whole point about Parallel is to run the work on individual CPUs or cores, and it have to be physical CPUs. So, for example, on my MacBook, I can get Parallel to use 4 cores nice and easily, and just basically make the most out of the hardware. That's the point about Parallel, to make the most of the hardware. Now, of course, if you've got parallel threads making the most of all of the CPUs, it could be pushing other threads off the CPUs so they don't get any time. I don't really know how the scheduling works underneath the covers. But you're not going to be, it's not going to be interfering with data on other threads, so it's not going to be reusing other threads and interfering with them from a data point of view. It might be stealing the CPU away from them, but I don't believe there's going to, you don't have to worry about things like about thread safety in the way that we traditionally had to.
Yeah, I think you're right here. And okay, let's move further. Probably the last question. Does IntelliJ IDEA provide suggestions to refactor from Yoda time to Java 8 time API? So I could try answer the question. IntelliJ IDEA doesn't suggest it yet, but there is an issue in issue tracker, and we still track votes, and feel free to vote through it, and definitely we can implement that.
Yeah, I really wanted to show some date and time stuff because I really like the new date and time API, but I didn't have any really good examples. I did see that there's the use of the obsolete date time API, but that's not Yoda time. That's the Java util date and Java util calendar.
Yeah, I think that's all we got. There are no more questions. In case you'll have other questions, feel free to ask them in Twitter or in comments. We'll be publishing the recording soon, and if you'll find some question not addressed, please share it with us.
Absolutely. You can always contact me over Twitter.
Cool. So thank you for your time.
Thanks a lot. Bye.
Thank you. Bye.